Welcome to you all to this MOOCs online video course Theory of Yarn Structure. In the last class we discussed about module 8 tensile mechanics of yarn. If you remember, in this module we started with mechanics of parallel fiber bundles. There we discussed about Hamburger's model. Then we continued with the stress strain relation in yarns. There we discussed about the well known Gegoff's theory, and also we little bit generalized Gegoff's theory by incorporating contraction ratio or Poisson's ratio in yarn. We will now start from there. The Gegoff's theory if you remember, the tensile force utilization coefficient phi was equal to cos square beta d, where beta d denotes the twist angle of surface fibers in yarn, right. Now, I ask you to think about Gegoff's equation. Phi is equal to cos square beta d. Think about this equation a little. Tensile force utilization coefficient is equal to cos square beta d. Are you able to find out any problem in this equation? Let me give you a hint. A yarn whose beta d is constant, that means the twist angle of surface fibers in a yarn beta d is constant for a given yarn. That means, for that yarn phi gives one single value. So, tensile force utilization coefficient in a yarn is constant according to Gegoff's equation. Mind it, this is not a function of yarn strain. So, if I plot yarn axial strain along x axis and tensile force utilization coefficient along y axis, then I will get a line which indicates phi is equal to cos square beta d, is not it? This is the interpretation of Gegoff's equation. What does it mean? Irrespective of the magnitude of axial strain of yarn, whether it is low or it is high, tensile force utilization coefficient is constant. Is it true actually? In order to answer this, we have to go back to the stress strain curves of fiber and yarn. Stress strain diagrams of fiber and yarn, how they look like. If we plot strain along x axis and stress along y axis, let us first draw a schematic stress strain curve for fiber, then we will draw the schematic stress strain curve for yarn. So, for fiber it starts from 0 from this position, then it increases, then somewhere it breaks. Suppose this is the breaking point. Typically the stress strain curve looks like this. So, this stress strain curve is for fiber. It starts from 0, initially it shows a linear portion, then it shows nonlinear. As the strain increases, stress increases, somewhere it breaks. So, this the coordinates of this point gives us breaking strain and breaking stress. How this curve looks like for yarn? For yarn, it is very much similar, but different in terms of magnitude. So, for yarn also it starts from 0, then it increases. However, it breaks earlier than fiber. So, this is a typical stress strain curve for yarn. What is the similarity and what is the dissimilarity between these two curves? The similarity is, look wise they are very similar. Both the curves start from 0, initially both the curves show linear region and then nonlinear, and both have breaking points. What are the dissimilarities? Dissimilarities are mainly on two aspects. First, the stress breaking stress for yarn, this value is always lower than the breaking stress of fiber. So, this is the first dissimilarity. Second dissimilarity is the breaking strain of fiber, this point is always lower than the breaking strain of fiber. Why does it happen so? in a short answer, the arrangement of fibers in yarn and the mutual interactions among fibers are responsible for this behavior. And there is another dissimilarity, that is, if we compare these two curves, then we see that as the strain increases, the difference between 2 points at a given strain, say at a given strain, this strain. So, this point and this point. So, the difference between these two, tensile stress of fiber and tensile stress of yarn, if we take another strain, say this point, if we draw a perpendicular line, then this point, and for yarn this point, this difference is not constant, what Gegop's model says. That means, the tensile force utilization coefficient phi is equal to tensile force on yarn divided by tensile force on fiber. This is not constant. Rather, this ratio is a function of strain. Let us now see the behavior of fiber stress utilization in yarn as per Gegop's theory. If we plot strain along the x axis and if we plot coefficient of fiber stress utilization in yarn along y axis, then in accordance with Gegop's theory we find a constant value of fiber stress utilization irrespective of yarn strain. Phi is equal to cos square beta d as per Gegop's theory. But experimentally we find a little different trend. We typically observe this kind of trend experimentally. What we observe here is that the experimental results are always lower than that predicted from Gagop's theory. So, a yarn always experiences a little lower value of fiber stress utilization experimentally as compared to Gagop's model. Why is it so? This is the question now. In order to understand this, we need to go back to Gagop's theory. We have already discussed Gagop's theory. This theory is based on ideal helical model of fibers in yarn. As you know, in ideal helical model, we assume the assumptions of helical model, that is, fibers follow helix inside the yarn, all helixes have same length, all helixes have same direction of rotation, that is the direction of yarn twist, and the height of each coil is same. So, these four were the assumptions of helical model. In ideal helical model, we introduce one more assumption, that is packing density inside the yarn at different places is constant. Also, Gagop's theory is based on linear stress strain behavior of fibers. Further, we assumed small strain of fiber and yarn in case of Gagop's theory. So, why these two trends are different? It might be possible that the assumption of ideal helical model, specifically mu is constant, is probably not correct. However, in many theoretical concepts, packing density is assumed to be constant. Second reason might be due to linear stress strain behavior of fibers. It is well known from experimental results of tensile behavior of fibers that the fiber stress strain curve is not linear. So, it might be possible that this assumption is giving this mismatch between experiment and Gagop's theory. Also, we assumed small strain in case of Gagop's theory, that might also lead to a problem. There is one more reason that is probably playing a role in this mismatch, that is related to fiber orientation in yarn. As I told you, Gegoff's theory is based on ideal helical model, where there is a regular arrangement of fibers inside the yarn. That is the meaning of helical model. All fibers are helical, so there is a regular arrangement of fibers inside the yarn, but in reality fiber arrangement is not regular, it is quite random. So, different fibers have different angles of inclination from yarn axis. So, the arrangement, the directional arrangement of fibers is different inside the yarn. So, it might be possible because of this regular versus random orientation of fibers inside the yarn, this difference is coming. So, this may also be the reason of this mismatch. So, in order to now know more about this, let us learn about fiber orientation. We will now study about fiber orientation. Fiber orientation is a very important concept in theory of yarn structure. The structure of any material refers to the arrangement of its constituent elements. A staple fiber yarn consists of fibers. So, fibers are the building blocks of a yarn. So, fibers are the elements of a yarn. How the fibers are arranged, that basically helps to form the structure. Arrangement of fibers is often talked in two aspects. One is the directional arrangement of fibers, second is the packing arrangement of fibers. The packing arrangement of fibers is characterized by fiber packing density. In module 2, we discussed about fiber packing density, that means fiber packing arrangement in yarn, quite extensively. However, fiber directional arrangement we also characterized by coefficient Kn. However, it now needs elaborate discussion on fiber directional arrangement in yarn. So, we will first start about this orientation. What is fiber orientation? Though fiber orientation is a very popular terminology in yarn structure, however, its meaning is more intuitive. What does that mean? If you look the arrangement of fibers, then what we see is that we see a long length of fiber in a yarn or in any textile material, be it web, carded web or sliver or yarn. The fiber length is quite long. Suppose this is a fiber which starts from this point and it ends at this point. So, there is a fiber curve. What is the orientation of this fiber? So, fiber orientation or the fiber curve is different at different points. So, which curve we should consider to discuss about fiber orientation? So, that is why we said it is little intuitive. Let us take 2 points, ideally as close as possible on this fiber curve. We have taken 2 such points, capital A and capital B. Let us join these 2 points A and B. So, this is a joining line, there is an arrow which resembles a vector, orientation vector. So, it will have a magnitude, also it will have a direction. Now, so when we talk about these 2 points A and B, that means we talk about very small segment of fiber. So, when we talk about fiber orientation, precisely we are talking about orientation of fiber segment. So, what is this segment? Is basically 2 points as closely as possible on a fiber curve. Ideally speaking, this distance AB should be as close as possible, that means they should tend to 0. Why does it happen? You see, the fiber curves, they are very different at very different places. If this distance we take very close, very small value, then we will be able to get the real picture of fiber orientation. But if we take this distance quite large, then what we are doing? We are basically getting the averages of all those small orientations. That means we are losing many more information. That is why in practice also we should take this distance as small as possible. Theoretically, AB, the distance tends to 0. That is why we also call it as unitary vector. So, orientation unitary vector, because these endpoints are should be very close and it is the tangential direction of this. So, this is, so what happens practically? We divide this fiber curve into very small segments equal length, and we find out the tangent of those points. That gives the value of orientation. So, this is the meaning of fiber orientation. Because of this meaning, we said though fiber orientation is very well heard, however, its understanding is quite intuitive. Now, we talk about theoretical understanding of fiber orientation. Now, in textile industry, we receive bales of fibers. Often said, the fibers are isotropically distributed in those bales. Then we take the fibers, so we destroy their orientation, we form web, carded web, where the preferential direction, the modal direction of fibers is the machine direction, so it becomes anisotropic. So, from bales to carded web, from isotropic to anisotropic orientation. Then that carded web is turned to form sliver. Sliver also has an axis, and majority of the fibers follow that axis. So, that means there is also a preferential orientation of fibers in sliver, anisotropic. That sliver is used to form roving, roving is twisted to form yarn. So, roving is also an axis, yarn is also having an axis, and preferential fibers are directed along the axis. That means sliver, carded web, sliver, roving, yarn, everywhere fiber orientation is anisotropic. However, in bales we grossly assume it is isotropic. So, that means these textile operations are converting isotropic orientation to anisotropic orientation. So, we need to understand both these isotropic orientation as well as anisotropic orientation theoretically. So, we will now talk about models of fiber orientation. There are two models, one for isotropic orientation. Sometimes you will see it is also called as pure random orientation. And the second is an isotropic orientation. So, majority of the fibers follow one particular direction, that is why it is anisotropic. So, it is said as preferential direction or preferential orientation. In one direction, that is why it is called an isotropic. So, first we talk about pure random or isotropic orientation. Pure random orientation or isotropic orientation. The frequency of inclination angles of fibers is same at all directions. That is what is isotropic orientation. So, relative frequency is also same at all possible directions. When frequency is same, relative frequency is also same. When relative frequency is same, then relative frequency divided by class width is also same. Where from this class width comes? The class width comes from frequency distribution of random variable. You have probably done in the first few classes of a basic statistics course during your undergraduation, frequency distribution of random variable, class, mid value of class, class width, frequency, relative frequency density, relative frequency density. This term, what is this term? Relative frequency divided by class width. If you remember these terms, very good. If you do not remember, do not worry, we will probably solve a numerical problem where we will clarify all these basic things. Now, this relative frequency density has a very similar meaning with another term called probability density. Actually, relative frequency has a very similar meaning with probability. Therefore, relative frequency density is also interpreted as probability density. This probability density follows a function which is often known as probability density function. In short, we use PDF for this term. You remember the probabilistic characteristics of a random variable are expressed by two functions. One is probability density function PDF and the second is cumulative distribution function CDF. Now, in isotropic orientation, as the relative frequency is same, so relative frequency density is also same at all possible angles. So, probability density is same for all possible angles. That means, probability density function is a constant for isotropic orientation. Probability density function is a constant for isotropic orientation. What does that mathematically mean? In order to understand that, let us understand the practical aspect of this. Imagine a fiber segment or imagine a fiber, you divide this fiber into many small segments of equal length and you measure the angular disposition of these small segments from one axis. So, you get many values of that angle. Suppose that angle we denote by psi naught. So, this angle will lie from minus pi by 2 to pi by 2. That means, how is this angle? Suppose this is your x, this is your y. At this point, this angle we thought 0. Okay. From this point to this point we come. So, at this position phi 0 is pi by 2 positive first quadrant, but suppose we start from here and we come to this second quadrant. At this point this angle is minus pi by 2. So, there are the two extreme possibilities, it can be pi by 2 to minus pi by 2. So, all the angles will lie within this interval. So, this is a random variable, angle of inclination of a fiber segment from one axis, say yarn axis. So, it will vary from minus pi by 2 to pi by 2. So, using these angles, if we try to construct frequency distribution of this angle, we will be able to form certain classes, mid value of those classes, then class frequency, we will have relative frequency, we will have relative frequency density, that is relative frequency divided by class width. So, in isotropic distribution, isotropic orientation, the PDF is a constant, probability density function is a constant, because relative frequency is same at all possible angles. Let us denote this PDF by this symbol, it is a function. This constant let us denote as k. Do you know what is the value of k? Those who are thinking k is equal to 1 by pi are correct. Let us find out this value. What is the summation of all relative frequencies? Summation of all relative frequencies is equal to 1. So, 1 is equal to summation of all relative frequencies. For continuous random variable we use integration in place of summation. So, summation of all relative frequencies, integration of all relative frequencies. So, this is the frequency, relative frequency density, right. This indicates relative frequency density. So, if we multiply What is radial frequency density? Radial frequency divided by class width. So, if we multiply this with class width, we get the radial frequency, that is probability. So, class width is d psi 0, right. So, what is the lower limit? Minus pi by 2. What is the upper limit? Pi by 2, right. So, this expression is very simple expression. What does it mean? This means relative summation of all relative frequencies is equal to 1. That is what we actually wrote mathematically. Now, let us work with this equation, minus pi by 2 to pi by 2, this is equal to k. So, k times d psi 0, d psi 0 is the class width, k is the constant. K is a constant, it will come out of integration. So, 1 is equal to k times d psi 0 minus pi by 2 to plus pi by 2. If you solve this integration, psi 0, integration of dx is x minus pi by 2 to pi by 2. So, k pi by 2 minus of minus pi by 2, right. So, k times pi. So, what is the value of k? Let us write here, k is 1 by pi. That is why I said those who were thinking k is equal to 1 by pi were correct. Right. So, if the fibers are isotropically oriented in a yarn or in any textile material, then you can expect the value of PDF, probability density function, is a constant, and that value is 1 by pi. So, this is what we understand from isotropic orientation of fibers. What is the second type of orientation we talked about? That is related to preferential fiber orientation in one direction, anisotropic orientation, that we will discuss now. So, anisotropic fiber orientation or preferential fiber orientation in one direction. Now, what happens during textile operations is, during processing, a fiber is influenced by surrounding fibers and also by machine elements. Machine elements means rollers, some pins, teeth of the opener, like that. So, there are basically two major influences that governs the orientation of fibers in any textile material. One influence is influence from surrounding fibers, second influence from the machine elements like rollers, pins, teeth, etc. So, these two influences actually dictate the orientation of fibers or the preferential orientation of fibers in one direction. Now, how do we model preferential fiber orientation in one direction, or how do we model anisotropic fiber orientation, or practical problem, fibers from bell to fibers in carded web, how the orientation is changing from isotropic orientation to anisotropic orientation. Is it possible to model this effect? So, that we will do now. So, we will follow a very interesting idea. The idea is related to an imaginary flexible belt equipped with perpendicular spikes. So, this model is based on this very interesting idea, imaginary flexible belt equipped with perpendicular spikes, where the spikes resemble the influence of surrounding fibers. So, we will now discuss about this model. We will consider first isotropic orientation, and these spikes resembling the influence of surrounding fibers will make it to anisotropic orientation. So, this model considers this particular phenomenon. So, we will start this model in the next class. Thank you for your attention.